So first take a look at the question. Now, in an ideal dual combustion cycle, the pressure, volume, temperature at the beginning of the adiabatic compression, they are given 93 adiabatic compression, yeah? So beginning of adiabatic compression, beginning means your point 1. So where should be your point 1? Then you have to look into the diagram afterward. 93 kPa the pressure, 0.05 meter cube the volume, and 24 plus 273 Kelvin, that is your temperature. So basically, when you look into this question, from the first, okay, they have given you all the three values: pressure, volume, and temperature. So what we need to do is we need to find the mass if they have given us all the data. Let's say, for example, here, okay, pressure, volume, temperature. Now the volume ratio, adiabatic compression, that means the volume ratio again is 9:1. Now the constant volume heat addition, pressure ratio, this here they give you a pressure ratio based on heat addition is 1.5:1, and then the constant pressure heat addition volume ratio is 2:1. So there are two heat addition here, two supply. One is based on constant volume, the other one is based on constant pressure. Both they have given us the ratio. One is pressure ratio, the other one is the volume ratio. And then at the beginning also they have given us a volume ratio based on adiabatic compression. So this is your PV and TS diagram. So for dual combustion cycle, you have one constant pressure process, 3 to 4, two constant volume process, that is 2 to 3 and 5 to 1, and two isentropic process. So you can see on your TS diagram, these two are the isentropic processes, 1 to 2 and 4 to 5. So that means there shouldn't have any heat flow from 1 to 2 and 4 to 5. Then when you look at 2 to 3 is constant volume, remember? Okay, 2 to 3. So this is a constant volume process. So the heat supply, because increased entropy here, the heat supply will be CV, T3 minus T2. And then 3 to 4, that is here, can see from the PV diagram, is constant pressure. And then increased entropy, so heat addition or heat supply, 3 to 4. So we have Cp T4 minus T3 for the heat supply. So the total heat supply should be Cp T4 minus T3 plus Cv T3 minus T2. Okay, so you have two heat supply here. Then the heat rejected should be 5 to 1, decreasing entropy, which is the constant volume, 5 to 1 here. Okay, so it should be Cv T5 minus T1. So the given values are the pressure, volume, and temperature. So we fill up pressure, volume, and temperature. This time we are correct. The volume is in meter cube. So the best is to find out the mass once you have got something like this, and the volume is in meter cube. So referring to the ideal gas law, you will be able to find out the mass for A. Okay, so this is for A. Okay, or they have given us the Cp value and the Cv value, yeah? So that means maybe it is a different type of gases. Okay, so no problem. So what we need to do is we apply PV equals to MRT for state point 1. We can find out the mass, the unknown mass, which is 0.055 kg. So once you have found out the mass, then the next thing is you can see this is your volume. So they have given a beginning of the adiabatic compression at the beginning of the adiabatic compression. So when you look at your PV diagram, compression is only 1 to 2. Okay, 2 to 3, no change in volume. 5 to 1, no change in volume. 3 to 4 is increased volume. 4 to 5 is increase in volume. So only 1 to 2 is a decrease in volume, and then this is an adiabatic process. So at the beginning, so that means this should be your point 1. This should be where it is located. And then they have given us the volume ratio here. That means V1 to V2 here, given as 9 to 1. So based on this volume, which we know, okay, we can find out the V2. So based on this, you will be able to find out V2, which is 0.0056. Okay, based on the adiabatic or isentropic compression. Then based on the relationship of pressure volume, because you have got this. So now it is time for us to find the pressure or the temperature by using the isentropic relationship between pressure, volume, temperature. So remember, this is gamma. So you can also find out gamma by taking Cp over Cv. Cp over Cv to find out your gamma, which should be 1.4. And then your P2 found 19.93 bar. Okay, so that is your P2. So basically the same thing, we have to fill up the entire table. Okay, because in addition, this question here, they have mentioned or they have asked us to find or to determine the pressure, volume, temperature at the cycle process chain points. That means 1, 2, 3, 4, 5. Okay, so we have got this. Now we have to move forward for the temperature T2. So you can see this is the only thing we need to know at state point 2. So therefore, you can refer to the ideal gas law at state point 2 only. So the ideal gas law, which is PV equals to MRT this time, not PV equals to RT, because you got the mass. Okay, so you got the temperature, 706.92 Kelvin. Okay, so this row also complete. So the next, okay, so state point 3. State point 3, you can see V3 equals to V2, correct? V3 equals to V2. So you have your V2 is 0.0056. So this will be 0.0056 as well. So you have got your volume. Okay. So and then the pressure. They have given us the pressure ratio. The pressure ratio during constant volume process. So pressure ratio also maximum pressure divided by minimum pressure. Pressure ratio during constant volume. That means this, not this, yeah? Okay, they say this one. So P3 over P2 equals to 1.5, which is given in the question, 1.5 here. So you will be able to find out P3 is 29.9. And we know that this is constant pressure, so P3 will be equal to P4. So straight away you fill up this. Okay, fill up this 29.9. So that means this two value is found. And then V3 we know already. Okay, V3 we have already known because V3 equals to V2. So straight away you can use ideal gas law based on these two value to find out the temperature T3. Again, ideal gas law. Okay, so you will be able to find out T3, 1060.4. For this, we know the pressure already. Okay. Then the next thing is they did give us a volume ratio during this pressure process, constant pressure process. Okay, that is 3 and 4. Okay, so the volume ratio, again, this is, okay, P3 equals to P4. Then the volume ratio is Vmax to Vmin, yeah? V4 to V3, which is given in the question. They say is 2 to 1. So V4 is equal to 2 times V3. So you will be able to find out your V4 here. Pressure P4 you know, V4 you know, then ideal gas law you will be able to find out this. Okay? So you will be able to find out T4. Okay, so and the same thing here applies here 5 to 1, constant volume. So 0.1 and 0.5 should have the same volume, yeah? So you got the volume for 0.5. So what you need is the pressure and the temperature. So we just do the same thing again. Okay, so the isentropic expansion process. Okay, V5 equals to V1. Okay, so that is why you wrote this. So and then, okay, the next one, isentropic process is 4 to 5. So 4,5 here is isentropic. You can see here 4,5. So you take power gamma 1.4. Okay. P4 you have already known. V5, V4 you have already known. Okay, you can find out your P5, 3.68 bar. Then the last step is to find out the temperature T5. Okay, that is 1165.72. So once you have got all the pressure, volume, and temperature, now it is time for us to find the heat supply and heat rejected in order for us to find the net work out, the thermal efficiency, the mean effective pressure, the gross work, the work ratio, and so on. So I have mentioned just now 2 to 3 and 3 to 4. These are heat supply. This is constant pressure and this is constant volume. So you can see here on your PV diagram also. 2 to 3 is constant volume. 3 to 4 is constant pressure. So this is constant volume and this is constant pressure. So CV T3 minus T2 here. Since you have got mass, make sure you multiply by mass. And this shouldn't be in kilojoules per kg, okay? This should be in kilojoules only, not kilojoules per kg. Sorry for my mistake. Okay, so the mass and the mass. So this is kilojoules only because you multiply by mass here. Okay, so CV, they have given us the CV value. Okay, then multiply by the temperature difference, the mass, and then the question has given us the CP value as well. Then the temperature difference. So you will be able to find out the heat supply. This is based on 2, 3, and 3, 4. Then the heat rejected is based on 5 to 1, decreased entropy, yeah? So CVT, so because 5 to 1 is constant volume, decreased entropy means heat rejected. So you have this multiplied by mass because mass is given. So heat rejected, 37.03 kilojoules also, not kilojoules per kg, yeah? It's a bit confusing, sorry. Then you can find out straight away your net work out, and it should be kilojoules as well. No kilojoules per kg. Okay. So your thermal efficiency, all kilojoules, yeah, 51.47. Desired output over required input. Then for the work ratio, remember this is net work, yeah. So you can we have our net work out just now, right? So you can just simply put it here. And then the gross work expansion. Okay, so you need to take a look at your PV diagram. Expansion. Where are expansion? 1 to 2 is not expansion, it's compression. 2 to 3 not expansion because it's constant volume. 5 to 1 is also not expansion because it's constant volume. So the expansion only 3 to 4. You can see increase in volume. Then 4 to 5 is also another increase in volume. So to find the area under this 3 to 4, which is a rectangle, you can use height multiplied by base. So the height is the pressure here, multiplied by the base, that means the difference between V4 and V3. And then for this part here, which is isentropic, for the work, you can consider CV based on non-flow. Okay, if you were to refer back to the table, during an isentropic process, what is the work done? It should be CVT. Okay, CVT. Since the mass, you multiply this by mass. Here we don't multiply by mass because the volume is already in meter cube. So don't go and multiply mass here because the volume here is already meter cube. Okay, so this one you need to multiply by mass because this is in kilojoules per kgK and this is in Kelvin. So you can multiply by mass in order to get your kilojoules. So this is your gross work. So net work over gross work will be 0.68. That is your work ratio. So the next thing is your mean effective pressure, net work again. So there is why once you find out your net work, there are a lot of things you can find. So then the length of PV diagram. So based on your PV diagram, the length would be here to here. So you can take the range between V1 and V2 to get the length of the PV diagram. So you've got a mean effective pressure, which is, okay, you can measure this in bar or kilonewton per meter square. It's kilonewton per meter square or in bar. So in bar, it should be 8.85 bar. Okay. Then the question, this question, they ask us Carnot efficiency as well. Now, Carnot efficiency, remember, is given by this formula, always the lowest temperature over the highest temperature. So you have to look into the diagram, which is the lowest, which is the highest. So our lowest, which we have found, is 297. The highest, you can refer back to the table. The highest, you pick up the highest temperature, which should be 2120. So you will be able to find out the Carnot efficiency, which always higher than the thermal efficiency. Okay, that's all, and thank you. Stay safe.